As a review, if you recall, this was either from lecture 1 or 2 last week, we looked at the signal of our imaging system from a point object. And so in X-ray, what we modeled that with was we pried the ballpoint out of a ballpoint pen and we stuck it into our imaging system. We made a picture of it. And so that's a very, very small point object. With MRI, for example, you could take a very small tablet of, say, vitamin E, you know, those little things that dissolve in your gut, and stick that in the magnet as a point source, right? So that's the point source. And so we're imaging this point source, and the picture we get looks something like this. It's a blurred version of that point source, right? And we called this function the point spread function. Here it's h of x minus x2, where x2 is where our point source is. Okay, we're going to look a lot today at what this function h is, the point spread function, and how we model it in imaging systems. Okay, and so the point source itself, we're going to model with a function called a delta function. And many of you who've done physics or differential equations or whatever have probably run across delta functions before. And a delta function is just a very sharp, high function, right? So it basically, you go along and it's 0, 0, 0, and then it has a very high value, and then very quickly after that it becomes 0 again. So it's a point. It's mathematically how we're going to model a point. And you say, well, how high should it be? You know, or how narrow should it be? Well, it's actually, in practical terms, it's going to depend on how narrow do you need it to be well under, you know, the dimension of your imaging system. So the function itself is defined by this equation. And everywhere in the xy plane, in the 2D plane, okay, of our picture, this function equals 0. Right? Except at one point. And in this case, when we just have x and y here, it's at 0, 0. It does not equal 0 there. And we'll say, what is the value of it there? Well, the value is given by this. If I have another function, f of xy, and I multiply that function times the delta function, and I integrate that product over the entire plane, it gives me the value of f at 0, 0. Okay, so this function has some non-zero value, and that value is such that when I integrate across, it sifts out the value of f 0, 0. Let me put this on. Okay, so this function is defined everywhere, right? It has a value at f 0, 0, and when we do this integral, that value is pulled out. And that's actually the definition of the delta function. So it's implicitly defined, right? Any questions about that so far? So visualizing the delta function, it's just a very narrow point of a function. It has a non-zero value, delta xy, at the origin, right? And everywhere else it's 0. And that's going to serve as our point source mathematically. We can move the point source in the plane by eta and psi, some distance along the x and y axis, and then the delta function you just translate, you know, where that non-zero part of the delta function is by eta and psi. Okay? So you can have a delta function anywhere in the plane just by putting these variables in the argument. Okay? There are related functions. There is a delta function that is a line of non-zero values, and this will become very important for CT, that we have a line of values in the plane that have non-zero, and that is usually, it's delta sub L, and it's, you know, a set of points in the plane such that when you integrate across the whole plane, it pulls out the function along that line, right? So the f of xy gets pulled out on that line. And we'll see in CT we can parameterize where this line is with L, which is a distance from the origin, and theta, which is an angle of the line. And that implicitly defines a set of xy pairs that gives you, that's just an equation for a line. Another way to write it, right? For equation for the line. And then there's the sampling grid. And a sampling grid is a whole set of delta functions, right? And they are separated by a constant separation. So if we have a collection of delta functions, one at the origin, and then the next one is at y equals 0, x equals 0 plus delta x. And that's this one here, and then delta 2x is here, or 2 times delta x is here. That whole array of those is called a sampling grid. And you can imagine how this is quite useful because our picture is on a grid, right? And so we can model what's happening at points on this sampling grid. Okay. A lot of what imaging is about is when you sample stuff. You know, when you sample a function, how far apart should your samples be in order to reconstitute that function accurately? And then also, how many samples, how long should this grid be in order to sample appropriately for what we're trying to image? And so this has its delta sub s, which is the sampling grid. It's a function that's continuous in x and y, and it has 2 parameters giving you the separation of the sampling points in x and y. Okay. So moving along in our dictionary of functions that we're going to have to know, and I'm not kidding, you need to know all these functions, inside out. You should just, you know, when you have an hour and you don't have anything to do, just play around with these functions. Like find out like what they do, how they change, how they're related, okay? So these 2 functions, and we'll go into the details of this, we're just introducing them sort of as a dictionary right now. These are very useful in imaging. The first one is called the rect function, and it's given this symbol. It's not terribly creative, but and it's 0 in 1 dimension. It's 0 until you get to -1/2, and then it becomes 1. And then it stays at 1 until you get to 1/2, and it becomes 0 again. So its width is 1 unit, whatever x is, right? And its height is 1. That's called a rect function. So it's almost just like a gate, right? It's on inside that -1/2 to 1/2, and it's 0 everywhere else, right? So that's sort of, in terms of the second most simple image we can make, it is a good candidate, right? The first most simple image we can make was a point. We'll just put a point in the scanner. The second most simple image we can make is like a disk or a square, right? So if we put a disk in the scanner, across the face of the disk, say it had a diameter of 1 unit, and we stick it in the scanner, our image should come out a circle with a diameter of 1 unit, right? And you would characterize it by this function. As you went out in R, you know, you would have a positive signal, and it would drop to 0 when you're outside the circle. So that's kind of the second most simple picture you can make, all right? This function is quite interesting. It's called a sinc function. And you know, it has a 1/x term in the denominator and a sine term on the top. So on the numerator, you've got sine pi x. So it's just oscillating as a sine wave does, right? However, as it's going out towards x being big numbers, right, the 1/x term makes it attenuate down to a very small function. And so as you move away from 0, it attenuates rather quickly as 1/x. So it's like a sine wave that is being attenuated as you move away, right, as 1/x. And you know sine of x is an odd function, right? So it should come down and it should be 0 at the origin. It should come down and cross through the origin, and it's an odd function like this. This is obviously not an odd function, it's an even function because its sine is divided by x, which is an odd function. So now I got an even function, and lo and behold, when you take the limit of sine x over x as you approach the origin, the limit goes to 1, right? So now I've got a peak, right? So don't get thrown off by the fact it's sine and you think, oh, this must be an odd function, right? It's actually an even function. It has a central peak, and then it decays away as we're crossing zeros with the frequency determined by that sine function. Okay? So it's like a sombrero, right? You have a peak in the middle, and then it goes boom, 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 outside. And you see in all sorts of physics, right, and all sorts of optics, functions like this, right? You see that there's a central peak and then these sort of rings that are outside it that ring down at a particular frequency. And so it's used a lot. These are really cool functions to know and understand really well. And the other really nice part about these functions is their Fourier pairs. So the Fourier transform of this thing is this, right? The Fourier transform of this thing is this. So those two things go, they're called conjugate pairs, and you're going to use this a lot, right? The Fourier transform of a rect function, right? And so what does that mean again? So if I want to build this function using sine waves and cosines as, with a Fourier expansion, the amplitude of my coefficients go as this function. So I have constant amplitude out to this spatial frequency, and then it drops to 0. So it has only a finite number of spatial frequencies that are needed to build this function, right? And we're going to look at Fourier decomposition in some detail. How many people would say they're very familiar with the Fourier transform? And put your hand way up if you're really familiar with the Fourier transform. Okay, so we'll spend a little time on the Fourier transform. It's a marvelous thing. It's a great way to express functions and to understand the world, actually. Like when you look at something, after you get it, you kind of look at things and say, what is the spectral composition of that thing, right? And it actually makes a lot of things quite clear, right? When you understand, if you look at something and you understand its spectral composition, which just means what are the spatial frequencies involved in making that thing. In audio, it turns out like what are the audio frequencies in my signal, right? And the Fourier transform of an audio signal is the frequency components in that signal. And that's what your ear basically pieces out those frequency components and gives you a sound that's a cello or that's a tuba or that's Kanye or whatever, right? So it's pretty remarkable how good you are at say a voice, a human voice. I guess we're really tuned to it, our brain's really tuned to it, but like when you hear somebody's voice, oftentimes you know instantly who that is, and that's all just frequency decomposition of that person's voice. And it's being done by your ear-brain combination, right? So these functions exist also in 2 dimensions, quite simply. You can create a 2-dimensional rect function just by multiplying 2 1-dimensional rect functions together, and that gives you a square at the origin, right? And the distance along each side of the square is 1, and its height is 1. Everywhere else it's 0. So that's a square. And its Fourier transform is this sinc function, which in the plane looks like this. So it has this peak, and then as you go out, it decays away. It decays away faster along the diagonal, right? And it decays away here on each axis. Again, you can create the 2D sinc just by multiplying 2 of them together, right? So they're separable. Okay? So we're going to use a lot of 2-dimensional rect and sinc functions in the course. Also used in the course a lot are complex numbers, and the reason for that is it's a really convenient way to encode something that has both a magnitude and a phase, right? So all of the points on this circle that have this amplitude z have the same magnitude, but they all have a different phase. And so it turns out in magnetic resonance, the phase of the signal is tremendously important, right? And so a lot of what we'll look at is how you do quote-unquote phase encoding in MRI. And so you really need to be facile with complex numbers and how manipulating complex numbers is done, like multiplying complex numbers, dividing, etc. Okay. They came. You probably first saw them in high school when you did roots of an equation, and there were no real roots, but it turns out there's complex roots that if you admit that basically I squared equals -1, then you get a whole set of other roots for the equation, and those roots exist in the complex plane, not just on the real number line. So basically the magnitude of a complex number is, just z bar, so it's the Euclidean Pythagorean magnitude here. And its phase, this phase angle, is just the arctan of the imaginary over the real part right here, and it's, in this case, it's 63 degrees. This is the definition of I or J. In electrical engineering, J is used a lot, so we'll probably use J in this course. I think we use J pretty well all the way through here for the complex numbers. And J squared is -1. And here's two complex numbers multiplied together, right? And this is how you just do the multiplication as you would normally. And you get a real number, in this case, of 13. And so it turns out that these two numbers, when they're multiplied together, because they're complex conjugates, when you multiply them together, there is no imaginary component left. It's on the real axis, and it's 13. Okay. This is a fascinating and wonderful equation. This is actually, people who've studied physics and math for 40 years will say this is the most beautiful equation in math. It's just ridiculously gorgeous the way it works out. And you're like, why the hell is this true? Like when you first look at it, right, you're saying this number, who knows what this number is, just to a few decimal points. That's 2.718 blah, 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 right? It's like the compound interest number, right? So if you compound interest tighter and tighter and tighter, the maximum earning you can get is like 2.718 of your original investment, right, over that compounding term. You're like, well, okay, well, that makes sense. And e to the exponent j theta is equal to cos theta plus I sine theta. So what the heck does sine and cos have to do with that number, right? Because this is just like projections of a vector onto the unit sphere, right? I think the best way to like simply say that this is true, like why does it work out, is to write out the Taylor series of this one and write out the Taylor series of these guys and convince yourself, oh yeah, that's true. Those two series are the same, right? And so anyway, we have this marvelous compact notation now for generating functions that have, cosine and sine temporal or spatial dependencies, right? So things that are oscillating, we can just write them out as e to the j theta, where theta is that phase term, right? And this makes the math really trivially simple in many ways, right? The fact that you can do this. Again, here's e to the j theta. The cos term is here. This is the imaginary component. J sine term is on here. And so e to the j theta is just, in this case, the value is 1, the magnitude in it, and the theta just takes it around the complex plane with a specific phase. You can do it in reverse and say that cos of an argument is just the real part of e to the j theta. In this term, this notation changed here. So this equation is equivalent to cosine, and the sine term you just pull out the imaginary component of e to the I x in this case, and this is equivalent to sine theta. Okay, so it's in sort of the reciprocal function. And we'll see that there are cases, for example, when we derive the sinc function, right? You'll see that in the integral that we derive the sinc function with, this term comes out as sine theta or sine x, right? To show us that. So get to know Euler's equation. And then this is right out of the book. Unfortunately, this notation, this is supposed to be up here in the argument of this e to the j 2 pi times all this stuff up here. When we express that in terms of sine and cosine, it looks like this. Right? So we have a cosine 2 pi times some number, right? That is the sum of all this stuff together, right? And so that is an oscillation, just a cosine oscillation at that frequency, right? And to get that number, we have, 4 independent terms here: a u naught and an x and a mu naught and a y. And so that gives us a function that has oscillations along the real axis and oscillations along the imaginary axis. Okay? So let's take a look at some of those. So if this is, the 2D plane, and I ask, well, what do the oscillations look like with this argument, the mu naught x and the mu naught y? Right? If this is the xy plane, if I set this parameter mu naught to 1 and this to 0, I'll look back at the equation. So this is 0, this goes away, and this is 1, so it's just sine of 2 pi x is the function everywhere in the plane. That's what its value is. So there's no dependence in the y direction. It's just if I drive along an x direction, I get a sine wave. And the frequency of that sine wave is 2 pi mu naught. Right? If I double that, I just double the frequency of the sine wave, okay, in that direction. Still don't have anything in y. Higher frequency, again, I just double it again for that example. Now, the interesting stuff happens when you actually make mu naught not 0. We still have a plane wave of a specific frequency. That's called a plane wave that's oscillating. It's just tilted now, right? And the angle of that tilt is proportional to the ratio of these frequencies, right? So this frequency along here we can calculate as the magnitude of this pair, right, as we're going along with the sine wave. And if I add another, like I double the value of mu naught here, the angle goes up, and then when they're equal, I'm at 45 degrees, right, of the plane wave. So it turns out that when we're building two-dimensional functions with Fourier coefficients or sine wavy kind of things, these are the basis functions we're going to use. Some will have oscillations just in a single direction, but will tilt and have a set of functions that have an oscillation in that angle, tilt again, a set of functions that have oscillations in that angle. So we cover all of that dependence, spatial dependence, when we do it in 2D. So, the really cool thing about MRI is that what you do to your object before you take data to image it is you impose one of these patterns on the object. So we create a signal that we're going to measure back, but before we measure our signal, we use gradients, magnetic field gradients, to actually place one of these patterns into the object. And then we listen to the signal. Right? And so if this has been placed in the object, you will get a different signal than this and this. And it's essentially the physical embodiment of the Fourier coefficients of that object, right? Come out of the scanner. You physically put these, they're called k-space vectors or spatial frequencies into the object before you make your sample, take your samples. Right? So we're going to go into that in great detail, so you don't have to understand that right now, but that's just sort of looking ahead and why plane waves and understanding this are important, particularly for MRI. Yeah, this, unfortunately, those of you who read ahead, I emailed Jerry about this last year, and I emailed again this year, and he said, yeah, I'll talk to the publisher. He doesn't use the red shelf version, but in the red shelf version, this is supposed to be a script S, and then all the way through this section, this symbol pops up. Who knows what it means? Is it okay to say what it means? I have no idea what it means. Nobody knows? No. Looks. It's S in Chinese or something. I don't know. But anyway, sorry about that. Apologies extended. But just, it should be a script S. And so we're characterizing in linear systems the input-output equation, or like what is the output of our linear systems when a specific input goes in. And so we're going to characterize our system, our imaging system, with some set of functions, what we'll call S. This is the input. So the input is the actual object, the true object, right? And then this is the output. So whatever we do to the true object, this is what we measure. Okay? So an example is when we shoot X-rays through a true object. Say it's a two-dimensional density, right, map, and then when we collect those X-rays, I have a fairly low-resolution detector that, say, blurs the actual image itself. Then that blurring would be, mathematically described by this function S, and my output wouldn't be the true object. It would be some version of the true object that's blurred. That's pretty well how this is going to go. And we're trying to evaluate for each type of imaging system, what is this S function? Like, what does it do to the object before we see our picture, to understand the underlying spatial resolution, and etc. There's a few definitions that, this is really dry, but you just have to know it, that a linear system, right, S, so if our imaging system and we want to characterize it as a linear system, then this property is true, that if I have multiple objects, right, and I weight them, so say I multiply one of the objects by 2 by making it a thicker layer, and then I have the object as a single layer, etc. So I have some weighting here. I can take the individual output of the true object and multiply the weights after it goes through the linear system, right? After it goes through S. So just in like linear equations stuff, you're probably pretty familiar with this kind of thing. And that if you add everything up and put it through your system, it's exactly the same way as putting everything through your system and then adding up the results. Okay? So that's the definition for us of linear system. And so here's a picture. Here's our input. This is one of our simple, functions. This looks like a disk, right? It goes into our linear system S, like that we're going to characterize mathematically our imaging system with this S thing, this S function. And then out comes the picture, right? Which is G. Sorry. Okay. This guy, well, let's not say it's a disk. Looks like we're pretending it's a delta function here. And we're going to also say, well, a delta function with 2 parameters, eta and psi, can appear at some other point in the plane, displaced eta and psi, right? Or eta and psi. And so that means that our system right, if we're going to characterize it with a point spread function, we perhaps need like a point spread function that has a lot of parameters, right? If I need a different point spread function for a dot that's coming in this part of the field of view versus a dot that's coming in this part of the field of view, then this function, which is the point spread function here, gets pretty complicated, right? Because you have to account for the fact that where your object is coming from. And you can think of imaging systems, right, where it is true that the quality of the picture that's coming through is not the same for every point in the field of view, right? If you have a set of lenses or something and there's distortion and blur as you move away from the center of those lenses, well, basically the system function will, on the edges there, will not be the same as it is in the middle. Right? Yeah?
Is that why you do pump the person with the characteristic Fourier signal so they kind of baseline?
Yeah, interesting. So the question is that why you impose these Fourier coefficients or Fourier patterns on the patient before taking the signal in MR? And in fact, in MR, usually the system is, what we're going to see is shift invariant. It actually doesn't matter where you are in there, right? And in order to get the same resolution. However, in CT, it isn't shift invariant. And the reason is, like, if something's at the center and you're taking projections through it, the density of data, of projections at the center is better than out at the periphery. And so the point spread function might change out at the periphery. But for most of the analysis of an imaging system, you assume it's linear shift invariant, which means that if my dot is over here or it's in the middle, I'm going to get the same blur of that dot. And it just makes life mathematically a lot simpler, right? And so then it's like future graduate work to take the next step, which is, okay, what happens out, 15 centimeters outside my, ring of truth, inside this CT scanner. So what we're going to do is we're going to get to the fact that we're going to model things probably as linear shift invariant. Our output in general, right, is the input, our true like dot or our circle or our person, whatever it is we're imaging, it's a 2D function, multiplied by the point spread function at each location, right, in that field, and that thing is integrated over all those locations, right? And so the value of our picture at an XY point is actually dependent on the object everywhere in the field of view, right? The value at a single pixel XY is proportional to the integral over the entire object times this point spread function, right? So if there's blur, that means at a dot on my resulting picture, that dot is composed of signal coming from space around it, right, around that dot. And that's described in this equation. If this function, h, which is our imaging point spread function, if this is really super narrow, or if it's a delta function, then basically this and this are the same thing, right? It just sifts that point out, and we got a perfect picture. That's not the case. Usually what happens is we have to integrate over the entire object and look at how all of those pixels affect the one pixel we're reconstructing. If you assume that h is independent of position in the plane, right, then you can just use 1h for the whole thing, right? One point spread function can be used over the entire integral calculation. And then this complex function, which has two independent variables, which are over here, and two parameters, becomes essentially a two-dimensional function that is just proportional to the distance away from 0 of the point spread function origin, right? And so that's a big simplification and a big assumption. Right? Now the equation, instead of having all those parameters up here, this is truly just two variables, right? And all of these h's, regardless of where you are in the plane, are the same, right? Instead of having the eta and the psi causing you to have a different h everywhere you perform this integral, right? So this is called a shift invariant imaging system or a shift invariant linear system. And the great thing about that is if that is true, then this is true. And this means that your image is purely just the convolution of your object with the point spread function. So that's a really simple thing to do, right? You can do that in microseconds in MATLAB, just whoop, and you're done. You don't have to do every individual sort of feeding in with these different point spread functions depending on where you are on the plane. You can just do a convolution and you're done. This is a pretty powerful concept, right? It just says if I can characterize my system as providing, just a specific blur on a point object, then I can calculate what every picture is going to look like just by doing this convolution. So to remind you what convolution is and what cross-correlation is, and you can look at autocorrelation if you so desire. But a convolution, remember you flip the variable that you're integrating across, you put a negative in front of it. And so if I convolve f with g, right, what happens is we flip g around, the independent variable here, and then pass it across f, right? We do that, we move that variable along. And I'm going to get an output, which is the function of a 1D variable x, right? And at each point, the output is what occurs when I multiply g times f and integrate under that multiplication, right? So when they're entirely overlapped here, this will be the integral. I've multiplied this sort of top hat with the triangle. That's the integral, and that's the height of the function. And then as I move this along with this variable x, which I'm plotting, the integrals drop away as the two objects separate. And so the convolution of f with g, this square turns into that thing. Right? That's what a convolution is. And in general, what happens is we get an object, and the system that is the point spread function for our system is usually something like a Gaussian function, and it just blurs the object, and we get a blurred version of the object. In MRI, the interesting thing is the point spread function is actually a sinc function, because you take data out to a certain dimension in Fourier space. When you're multiplying the patient by those sine waves, you can't do an infinite number, right? You stop eventually. And so you have basically limitations of spatial frequencies that you've acquired. And that rectangle, when you do its Fourier transform, that's a sinc function. And that turns out to be the point spread function that you convolve the object with. And that has implications down the road. So that's convolution. Cross-correlation will show up in the definition of the Fourier transform. And it's the same as convolution, except you don't flip g around. Okay? It just stays in its original orientation and goes across the object. So you get a different function coming out, right? The cross-correlation versus the convolution. So we're looking at linear shift invariant systems, and then a couple of properties that come out if you can characterize your system this way is that if you have a cascade of systems, you have, say, one detector gives you some output, and then the next detector gives you another output, right? So I have two detectors back to back, like X-rays turn into photons, and that gives me a photon image, like a a light image, right? And then that image gets turned into electrons by photodiodes. So there's two systems back to back. Each one of those is going to introduce some kind of blur. And so this back-to-back cascaded systems you'd like to model. And if they are linear shift invariant, it doesn't matter what order they happen. Right? So you can blur it with the light first and then blur it with your detector next, or if it was done in the opposite direction, it wouldn't make a difference. And so these cascaded systems, whether you do one like H1 then H2 versus H2 then H1 with your input to get your output, doesn't matter. And in fact, this whole thing can be modeled just by convolving those two functions to get one function, right? And so if I have a cascade of a blur and then some other reason I'm blurring it, all I do is convolve those two H's, and that's my total blur on the picture. It's nice. It simplifies, the output. And then as basically a result of the linearity, if I go through this one and the output is the sum of those two outputs, then you can sum the two point spread functions and just use that as your point spread function. Okay. Separable systems are worth knowing, or like this concept is worth knowing about because it happens a lot in MR. And if you can write down, a point spread function as two functions that are just a function of x and just a function of y, then it makes your life somewhat easier, right? Because you can do operations, with this one first, right, in 1D, and then do operations with this one next in 1D. And you don't really have to do a 2D convolution, for example. You can just do two 1D convolutions. So if I have basically I'm looking for my output, g of xy is going to be my final image. Excuse me. And this is, my input is, fxy. The first thing I would do is convolve my input in one dimension with h1 along here, and that would give me a function, wxy, which is an intermediate function to get to the 2D function, right? I plug that one into the next blurring or convolution in the y direction, and I get my final output. Okay? And so that's only true if the point spread function can be expressed as the multiplication of two 1D functions. Okay? And we saw in one of the first slides that sinc xy can be expressed as just sinc x times sinc y. Right? So that's handy. It's in the old days, like when I started medical imaging, computational time was kind of an issue, for a lot of these things. Not so much anymore. Like Fourier transforms and everything like that are pretty well done instantly in whatever dimension, and especially at the dimensions of MRI, which are usually under 1K. You've got like 512 points or 256 points or something like that. So that stuff is all done instantaneously now. But back in the day, right, when you used to just have array processors, and they were kind of 1D array processors, this was very helpful to get things done quickly, these 1D procedures. So here's an example of convolving a 2D function, and this is the function at full resolution. So we'll call this fxy, where f is the brightness of a point at xy. It looks like this. It's a sagittal image of somebody's brain and their tongue and everything else. And then the intermediate function on our way to that 2D convolution is the blurring in this direction, right? And you can see that if you look at the sharpness of the nose here, it's blurry in this direction, but if I go off the top of that person's head, it's still not blurry in the y direction, right? So all I've done is done the convolutions this way, and then you do the convolutions that way to this as your result, and you get the 2D convolution. Okay. Okay, so we're going to introduce the Fourier Transform now. First, any questions about that so far? Let's pause for a second and see if we got any questions there. All right. I encourage you again to read chapter 2 multiple times. So this is the definition of the Fourier transform, and we can see some elements that we've already introduced. This is the e to the minus ij something. So this is a phase term, right? That's a phasor there. It's just holding place for the cosine and the sine terms that are used in doing a Fourier transform. And the inverse Fourier transform, if I take the output of this Fourier transform, which is another function, another 2D function, and it's in the conjugate variables, which are mu and nu, this is in space, 2D in like position in terms of centimeters or something like that. And these variables are cycles per centimeter. They're oscillations, right, or frequencies, spatial frequencies. So that's another 2D function. And I can take that 2D function, take its inverse Fourier transform, which is exactly the same as the Fourier transform, except that minus is missing here. And I get my original function back. Right? So these are called Fourier pairs, these two functions. This is a very important equation for many reasons. Like for just enjoying life, it's good to know this equation because you can think about things in the frequency domain as well as the spatial domain or the temporal domain for music and stuff like that. So it's good that way. Another reason it's good for this course is that this equation is essentially the imaging equation for MRI. The only thing that's going to change is that these variables will be explained in terms of things we do with the machine, right? So these variables are going to be dials that we're clicking around on the machine, right? But otherwise, this is the imaging equation for MRI. So it's really good to know this thing, okay? And in MRI, this is your object, and this is the raw data, right? It's an inverse Fourier transform, it turns out, to get, from the... Oh, I'm sorry. Scratch that. My bad. I went all the way. This is actually our raw data. This is our object. This is how we reconstruct the image from the raw data. Like reverse back and erase what I said before. Okay. So what's the next slide? Okay. So if we look at it, well, let's look at it in 1D. Because it's simpler to look at. And it's also more, I think, more sort of visceral when you think about it in terms of time and frequency. So everybody knows what a time domain signal is because you hear it, right? So the note A440 is 440 vibrations per second, right? So that's an oscillating signal. And in your stereo system, used to be you'd put a needle in the groove, and the groove would be moving back and forth at that frequency, and it would cause the speakers to move at that frequency, right? And when you looked at that would be the temporal function. So my microphone, I get a voltage that I plot, and that's the function in time. And then I can take the Fourier transform of that temporal function, and I get the spectrum of that temporal function, right? So if it's a tuning fork going at 440, and I put my microphone up and I look at the function and I sample it, it's probably going to be a sine wave at 440 if the tuning fork's right and it's a clean one. When I take the Fourier transform of that, this function basically is zero everywhere except at 440 hertz, right? So it's got a peak, a spike at that frequency. Now, the physics of making metal tongs vibrate and everything, there's probably higher harmonics in there that gives it actual tone. If, say, a violin plays A 440, right? You recognize that as a violin, and when you put the microphone there and you look at the voltage as a function of time for that signal, it's more complex, obviously, than that tuning fork. It still has a primary frequency at A440, but there's other stuff going on. And those are called overtones, and they're created by higher frequencies of that string, right? The box itself is vibrating and providing different frequency components. And so when you take the Fourier transform of that time domain signal, you get a spectrum, and that spectrum is characteristic of a violin, right? And that's how you, as a human, listen and go, ah, that's a violin, right? One assumes you decompose it into those spectral things. Maybe. I don't know. Maybe that's not true. Has anyone else got a better theory? Oh, you know a violin? Just from the tempo stuff? Just say, oh no, it's deep learning. It's not Fourier transforms, it's deep learning. It might be, right? Just like, oh, I've heard that before, and you just correlate it with something you know. But so anyway, if you have the Fourier spectrum, right, of the object, right, you can create the time domain signal. You can recreate the time domain signal by taking the inverse Fourier transform. Okay? For imaging, all we're doing is saying, I have a function in space, right? And the brightness of my function changes as a function of x. So it gets bright and dark, bright and dark, oscillates up and down. I take the Fourier transform of that thing and I get its frequency components, the spectral components of that spatial signal. And these are usually written k sub x if it's in the x direction, and k is called the spatial frequency, which is in cycles per meter or cycles per centimeter. Right? It's a frequency as a function of position, or it's a rate of oscillation of the intensity as a function of position. Okay. So if we look at how the Fourier transform is computed, so this is the equation. We expand this out, right, with the Euler formula, such that we have a real part and an imaginary part to this integral, right? And note the integral is taken over an infinite duration. So this is obviously modified to a certain extent in real life because we don't have an infinite signal. Right? We have a sort of finite signal. So these usually have finite integration. But when we do that, we take the raw signal itself, and at a specific value of kx, so here we are, we just set that value, right? We're going to make a function that's a function of kx. So let's just pick a value of kx, and then we'll run this integral with that value subbed in here. Right, see what happens. Okay. And if gx itself as a function has components that are very close to kx, right, then this integral will start adding up. We'll get a non-zero value. Right? And so this is how we basically, by cross-correlating sine waves with the function itself, pull out the components of that signal that are at that frequency, right, through this integral. Similarly, this is the even part, this is the odd part, this gives you a phase term. And so it's this part of the Fourier transform, it's the part of this signal, this oscillating signal that looks like a cosine, and this part of the integral, this whole thing here, is the part of this signal that looks like a sine. Right? So it's just shifted by a phase shift.
Excuse me.
Yeah.
Just a question. So the even part, like you said, it as x is closer to x value, it becomes bigger. So does that mean that it's getting magnified at that point?
Well, let's do this example. Say g of x, the function that's oscillating, is basically equal to this, right? At that point, those two functions are adding up at every point, and you're going to get a huge value, right, for this.
But that's only like that one point.
At that one point.
Everything else is uniform cost width. Like,
right. And so this, the way this is done analytically, obviously kx is a continuous variable, right? And so we get a continuous Fourier decomposition of this function gx. In reality, what's going to happen is we're going to look at discrete frequencies and how we can best reconstruct this function from discrete Fourier coefficients, right? And we'll look at that as the discrete Fourier transform. Okay. So let's look at a square wave, right? And this function, as a function of x, it just goes up to 1, then down to -1, then up to 1, then down to -1. And it has obviously a very strong relationship to the primary sine wave or cosine that has this frequency, right? So this, if we're going to build this function with Fourier coefficients, this primary harmonic is going to be a big one, right? And then as we add higher frequencies to this function, we start getting oscillations in the function, but a sharper edge here, right? So the frequency is sharpening up this edge. And then I add another sine wave at a higher frequency, but a reduced amplitude, and you get a sharper edge and more oscillations in the flat top part. And then as this goes on, this is the discrete composition of this function. As this goes on, and decays away, but goes to higher and higher frequencies, you can essentially reconstruct this square wave using those Fourier coefficients, right? When you take the Fourier transform of this thing, this function, so let's call this g of x, right? When you take that Fourier transform, the amplitude of these coefficients come out, right? That's what the Fourier transform gives you, is the amplitude of these coefficients and their phase. So let's do a couple of examples of computing transforms. And to some of those, for some of the functions that we've looked at already that are our big star functions. So here, this is just simply the plugging a function, delta x, right, into the Fourier transform formula. And the notation is, if I want to take the Fourier transform of a function, I have capital F stands for the Fourier transform. Everything inside the curly brackets is the thing I'm going to take the transform of. So here's our simple function back on our previous slide. G of x now equals the delta function. And so this function, remember what it looks like. It's 0, 0, 0, 0, and as we get to the origin, it shoots up to a high value and then comes back down at 0 again, right? When you do this, right, it sifts out the value of the function that's used in the Fourier transform at the origin, and that equals 1. So that means that the Fourier transform of the delta function is just 1. It's like a constant. For every value of frequency, its value is 1, right? So remember that, and we'll take a look in some detail at that. If you shift the delta function off the origin, you then sift out the value of this function at a position that's shifted off, so at a frequency that's shifted off, right? So you get that particular frequency as your output. And then the Fourier transform of the square wave, or the rect function, not the square wave, this is the rect function. Remember, the rect is 0 all the way to minus a half, goes up, and it goes back down. That's square wave is something completely different. This is a rect function. When we plug in the rect function into the Fourier transform formula, we get this integral resulting because it only exists between a half and minus a half, right? And then when you perform the integral, you get this result. And remember, this thing here, right here, that much of it is just sine of pi kx. And so this is sine pi kx divided by pi kx, which is sinc of kx. So let's look at it graphically. Here's the delta function at the origin in terms of what its value is as a function of kx when we take the Fourier transform. This thing, which is a function of kx, is 1 everywhere. Okay. And what that means is that a true delta function has an infinite number of frequencies required to reconstruct it. Right? So as I move out to higher and higher spatial frequencies, I need them all equally as much, right, in order to make this delta function. Right? So a true delta function never really occurs. Right? We get close approximation when we're doing imaging because it never really occurs that you can create an infinite bandwidth of frequencies. When I shift the delta function off the origin, what we get is a very interesting function that has unity. It's still 1, right, everywhere, but as kx changes, the phase of the function oscillates between the real and the imaginary component, right? So as a function of kx, it's still 1 everywhere. It's got phase as I move along as a function of kx. Okay, it oscillates with this frequency. Oscillates in particular with this frequency 2 pi x naught. And so if I move this farther out, this frequency increases. Right? If I bring it closer back to the origin, this oscillation decreases until finally when I'm at the origin, the oscillation is gone and it's a constant. So again, here's our rect function. It's 0 all the way up to minus a half, 1, plus a half. Plug this thing into the Fourier formula, and as we just looked at, we get this function for the integral, for this finite integral, right? And it's equal to sine pi kx over pi kx, which is the sinc function. Okay? So these are Fourier pairs. And we'll take a look at why the Fourier transform of this thing looks a lot like that, or is that. So similarly, if you take the output, what we found is the Fourier transform of the delta function, right? So that the Fourier transform of this thing is equal to the delta function. So as that thing is oscillating around, we pull out the delta function at that frequency. Okay? The Fourier transform of a cosine, so this is just the real part, it's just a cosine wave at a spatial frequency k naught. When we take the Fourier transform of that simple function, we get 2 delta functions. One at k naught, the frequency k naught, and the other at minus k naught, right? Where those 2 delta functions are non-zero. Okay? So I have a cosine function, take its Fourier transform. In the Fourier space, I have 2 delta functions. Okay? Similarly with sine, just you have a phase term on the sine function. The Fourier transform itself is a linear transformation in the sense that if I have two functions that are simply added together, I can take the transform of each function and then multiply by that constant. So the constant comes out of the integral. That's pretty straightforward because it's just that simple integral function. And it exists in 2D, right? So you can just do the integral in 2 dimensions and everything is the same. And now we'll look at duality. So the Fourier transform g of kx is this thing, right? So we have our function that's a function of position in x. Take its Fourier transform, we get this. It's a function of kx. So the similarity of these two things, right, where you show that the Fourier transform of this phasor that's going around as ax, which is a delta function, and the Fourier transform of the delta function equals the phasor just with a negative sign. And so these two functions are called Fourier pairs. And analytically, if you just write it down, if you remember anything, it's just the Fourier transform of big G of x, which is the Fourier transform of little g, is equal to little g again at minus kx. Okay, so you just flip the function around. So little g is the Fourier transform, or big G is the Fourier transform of little g. If you take its Fourier transform, you get little g back with the dependent variable going in the opposite direction. And that might sound terribly confusing right now, but it's not that confusing. We'll take a look at a couple of examples. So if you want to take the Fourier transform of the sinc function, right, we already derived that the sinc function was the Fourier transform of the rect function, right? So this looks like a very complicated integral, right, this guy here. But we know through duality that the Fourier transform of the sinc function will just be the rect function at minus kx, so with the axes flipped, right? And it turns out the rect function is symmetric, so that doesn't matter. So it's actually the rect function. Okay? So this is an example of a Fourier pair, this duality. And you should, in your head, have a whole Pictionary of Fourier pairs. Okay, so the first one to remember is the rect and the sinc function is a Fourier pair. So whenever you're working in one domain, spatial domain, you know what's going on in the Fourier domain because you know what its transform is, right? So it's always good to know that. And we'll take a look at a list of Fourier pairs. And there's about 8 of them you should know. And if you know those 8, you pretty well can do any kind of manipulation in both the spatial domain and the Fourier domain because you know what's going on in each one, right? You can approximate it. So here we'll just look at a list of Fourier transforms initially. So we already saw that a Fourier pair is the constant, 1, right, and the delta function. Okay? So we know that Fourier pair, and it's reciprocal. We know that the delta function, when it's displaced away from the origin by some constant, gives us this. It still has an amplitude of 1. However, it has a phase shift, right, given by that offset, right? The comb function is, remember, it's a set of delta functions in the plane that are separated by delta x and delta y. So it's a set of those delta functions. When you take the Fourier transform of that set of delta functions, you get in the Fourier space another comb function. Okay? And it turns out that it's just scaled by the separation here inversely. So if I make this separation bigger, right, in the spatial domain, when I look in the frequency domain at, let's just do it in 1D. Say I make delta x twice as large in the spatial domain. When I go to the frequency domain, this thing oscillates twice as fast. So I get twice as many per unit spatial frequency. So it's an inverse thing. As one stretches out, one contracts down in the conjugate space or the Fourier space. Well, we know this one here because we already did it, right? This transform pair and this. Sine of a plane wave gives us delta functions. Cosine of a plane wave gives us delta functions in the plane. The rect is sinc. Sinc is rect. The comb goes to comb up here. We already saw that. And then this one shows that a Gaussian function, like a Gaussian blob, when you take its Fourier transform, it turns into a Gaussian in the Fourier domain. So the Fourier transform of Gaussian is a Gaussian. If one Gaussian gets wider, let's say in the spatial domain our Gaussian gets very broad, then its transform in the Fourier space becomes more narrow. It tightens up. Okay. And here, this is a list of properties of the Fourier transform. And so we already looked at linearity. The translation property is basically the original Fourier transform times a phasor, right? When you translate your function. So if I have a function here and I translate it and look at what's going on in the Fourier space, the magnitude doesn't change, just the phase changes in the Fourier space. Okay? If you take the conjugate, of a complex function here, it's the conjugate in the Fourier space, but reflected around the origin. Okay? Then anything that is conjugate symmetric, so if I take the conjugate of something and it's equal to itself, like here, then it's a real valued function. Its Fourier transform is a real valued function. So that tells you if you have a real object and you take its Fourier transform, you know the Fourier transform will be conjugate symmetric, right? Reversing, scaling, you can look at these. This is the one that is tremendously valuable and useful. And I mean, they're all valuable and useful, but this is the one that's used all the time, and it's the convolution theorem. And that is, if two functions are convolved in the spatial domain, or in one domain, then in the Fourier domain, you multiply their transforms, right? And what that means is, let's think of it in terms of here's an object, and here's a blurring function, right? So I convolve my object with my blurring function, I get a blurrier picture. That's equivalent to applying a filter, right? It's basically a smoothing filter. And a smoothing filter, what it does is it takes the original Fourier transform of the object and multiplies it by the filter window, right? So in audio, say we have, frequencies from 1 hertz up to 20 kilohertz. And I look at my signal, and I say, you know what, I got too much noise up top here. I'm getting this really high frequency noise. I'll smooth this signal. And so in the time domain, you would convolve that time domain signal with say a Gaussian, and it would just smooth that signal in time. In the Fourier domain, it's equivalent to taking the Fourier coefficients of your signal and depressing the high frequencies. So it's it's a low pass filter, right? So a low pass filter is just a smoothing function in the spatial domain. And then this theorem shows that you can just do this in your head, right? It's great. So convolution modulation theorem, you can go through this yourself and prove to yourself that it's true. Finally, that the Fourier transform of the product of two things is just the convolution of their transforms. And this is used all the time because you think about smoothing in the spatial domain, and then oftentimes your raw data or whatever is in the Fourier domain, so you have to know what does it mean over here. Or if I do something over here in the Fourier domain, what does it mean in the spatial domain? Oftentimes what you're doing in the Fourier domain or your raw data is multiplying by some kind of weighting function, and that turns out to be a smoothing function. Or in MR, sometimes you're missing data in certain parts of the Fourier space, so you have to interpolate between positions. So you might do that interpolation with a convolution. And so convolving that raw data, when you look over in your spatial domain, you basically are multiplying the outside of the field of view down, right? So you just know that instantly by this theorem, right? And then we characterize the system. This goes all the way back to what we talked about in the first lecture. These systems can be quantified in terms of their ability to resolve small things, or what is their resolution, by the modulation transfer function. And the modulation transfer function is plotted in the Fourier domain, right? It's spatial frequencies, cycles per millimeter. So I have some object, it's got a certain spectral set of components to it. And that is like, does it have a really sharp edge? If it has a super sharp edge, I need high frequencies to reconstruct that sharp edge, right? Or if it's a really tiny dot, I need high frequencies to approximate that as a delta function, because that basically has an infinite set of coefficients. But the system itself, when you design an experiment and say, can I characterize my system's ability to resolve things, you end up with this function. It's called the modulation transfer function. It is how high frequencies are attenuated by your linear system, by your process, right? And this is what your raw data is multiplied by, right? And is this filter, so this modulation, it's attenuating high frequencies. And that's equivalent to doing a convolution in the spatial domain with the Fourier transform of this thing. And the Fourier transform of this thing is the point spread function. So you have a point spread function in the spatial domain, like a Gaussian. Take its Fourier transform, you get the modulation transfer function. And that's what the smoothing looks like in the spectral domain or the Fourier domain, right? And so this system can image higher frequencies than this system. Pictures from this one will be blurrier than pictures from this one, right? If you look at this is our object gxy. This is the magnitude of its Fourier transform. In fact, it's plotted as the log of 1 plus the magnitude of the Fourier transform for various reasons. If you just plotted the Fourier transform, all you would really see is the stuff in the middle here, because it's so dominantly high. So you take the log and you add 1 so that you don't get crazy log numbers. So this is all the information in here in the Fourier domain. If we multiply by an MTF that suppresses higher frequencies and then do the inverse Fourier transform to get our object back, it's a blurrier object. If we multiply by an even stronger filter, attenuating high frequencies out here in Fourier space, we get an even blurrier object. Okay? So the DC value, the zero value here, the zero frequency is just the average value of the whole thing. That doesn't change. But the ability to resolve these edges and these small things does diminish, right, as we multiply by these narrower and narrower MTFs or filters. Okay, so we'll stop there and we'll pick it up on Wednesday. Okay, and I'll be here. If you have questions, I'll stay behind. You can ask questions. Okay?